Okay, hello, welcome to the first in a series of video casts for A2 Computing. There's going to be a series of 11 topics that we're going to be covering, and our first topic is 3.1 hardware, where we're going to be looking at data transmission, communication methods, and communication on networks, communication standards, and the use of the internet. Okay, so first of all, let's start looking at data transmission. So data transmission is either data being transmitted between computers, data being transmitted between computers and peripherals, or internally on the computer, on the motherboard, linking back to last year on how the data can be transferred around the CPU. Okay, so the transmission format, data is often usually sent using the ASCII character set. So for example, A is 65, which is represented as 0100000001 in binary. B is 66, and there is the binary representation. Okay, so let's look at serial transmission. It's where there's one wire, one communication channel. So let's consider that to be one wire. Okay, so voltage is sent down the channel. To simplify things, let's assume that 1 is sent at a high voltage and 0 is sent at a low voltage. The bits are sent one bit at a time down the channel. So as you can see here, where's my mouse disappeared to? Okay, we've got the sender, and that's sending the bits in sequence to the receiver. Okay, parallel transmission is where we're looking at multiple wires. So for example, 8 wires can be used to send each bit of the character simultaneously at the same time. So if we look here, all of the bits for the letter E are being sent and received at the same time. And then all the letters for A are being sent at once and then received at the same time by the receiver. So the advantages of parallel transmission are more data can be sent at the same time. For example, with 8 wires, 8 characters can be sent at the same time, or in the same time frame that only one character could be sent with a serial transmission method. But it's not always the case that parallel cabling is faster than serial cabling. The medium that's being used is important too. So for example, fiber optic cables are serial, but are many times faster than most conventional parallel cabling, which uses copper wires. Okay. However, all things being equal, so if you have parallel transmission on fiber optic cables, then a parallel transmission on a fiber optic cable will be quicker than a parallel transmission on copper cables. Okay, so the disadvantages of parallel transmission are over longer distances, the bits can get out of sequence. Parallel wiring is more expensive, therefore parallel transmission tends only to be used over short distances, for example, inside the PC, the data bus, the address bus, and so on, and to connect printers and to other peripherals that are close by. Okay, so we've got simplex, half duplex, and full duplex communications. So in simplex communication, data is sent in one direction only. For example, a mouse connected to a computer. With half duplex, data is passed either way down the connection, but not at the same time. So this is used in some older networks, for example, up until the mid-1990s, and community broadcast radio is another example of this. Okay, and then we've got full duplex communication where data can be sent both ways at the same time, and most modern networks work in this way. Okay, so modulation and demodulation, that covers everything on parallel transmission, serial transmission, and simplex, full duplex, half duplex communication. So we've got modulation, demodulation. So we've got analog data. So the telephone network was designed to transmit voice and sound in an analog electrical signal. It was required to transmit computer data, zeros and ones, low and high frequency electrical values. So if we look at this sine wave here, okay, so we've got a high voltage here because the sine waves are closer together, and then as you're sending the zeros, sine waves become further apart. Okay, before broadband, modems were used. These converted modulated or these converted so modulated the digital signals from the computer into analog to send down the telephone line. They were also converted demodulated, the signals arriving from analog into digital. Hence the name modem, modulator, demodulator. So when we're looking at a digital signal, computers transmit data digitally with discrete electrical signals being sent with a high voltage representing a 1 and a low voltage representing a 0. So as you can see here, we've got a high voltage for a 1, a low voltage for a 0. High voltage for a 1, low voltage for a 0. So in the digital transmission of data, it's much faster transmission speeds are possible using digital data. For example, with broadband, typically it used to be 128 kilobit connection to the internet. Now we can be looking, my own broadband connection is about 30 megabits per second using a fiber optic connection, and there are providers out there that allow you to go up to 150 megabits per second. So there has been a significant increase in the speeds available. Digital data can be compressed and therefore transferred more quickly. Digital data can be error checked and therefore is less likely to suffer corruption or degradation. Keywords there, corruption and degradation. Make sure you get those written down. There's no need for a modem. We have the ISDN, which is the Integrated Services Digital Network. So this was widely used in the 90s and early 2000s, and it needed a special digital connection into the house or business. We now use something called DSL, which is the digital subscriber line, and this is what made broadband accessible to everybody. So we have ADSL, where you have a faster download than upload, and most home broadband connections are an ADSL connection. Then we have SDSL, which is symmetrical digital subscriber line, which has the same upload and download speed, but obviously you'll pay more for that because you're getting an equal upload speed as to the download speed. Download speeds are usually the speeds that we want highest at the home. There's also lease lines. These are similar to SDSL, but the line is not shared with others. It's more expensive but used by larger organisations. So here at the college, between the two sites, we have a leased line, which we pay somewhere, I think it's around £40,000 a year, to lease that line, to have one line between the two sites. Okay, so multiplexing allows several signals from different sources to be combined for transmission over a shared medium. Signals are combined at the multiplexer, MUX, and split at the receiver using a demultiplexer, DMUX. Signals are sent via different frequencies over the same line. Okay, so that allows computers on the network, for example, within the room, to share a single link. Okay, so we've got conversation A, conversation B, conversation C, D, E, all going down the same line, but at different frequencies. Okay, switching can take input from multiple routes and forward them down the appropriate route. Networks usually have multiple switches, and information can be passed from a source node, for example a computer, to a destination through various switches. And we will now look at two methods of switching: circuit switching and packet switching. So the best example of a circuit switch network is a telephone system. While two telephone lines or computers via modems are connecting, a single dedicated path is established between them. So we've got the telephone going through the network, okay, to the other telephone. The line is held open for the entire duration of the conversation, so when you're on the phone, somebody else can't chip in and have another conversation. Data is sent in order down the line. Okay, so imagine the phone conversation. It wouldn't make sense if things were all garbled because it wouldn't make a conversation. Even during periods of silence when no data is being transmitted, the line cannot be used by other computers until the call is ended. Essentially, it's just a massive waste of resources. Packet switching is used in most modern networks, including the internet. rather than circuit switching. Data can be transmitted across a packet switch network in separate blocks of data called packets. So the contents of a packet, most of the packet consists of the actual data being sent. It's usually around about 1.5 kilobytes in size. There is also the source address, so the address of the computer sending the data, the destination address, so the address of the computer being where the data is being sent to, the packet sequence number, so if the data is being split into multiple packets, the first packet would have a sequence number of 1, then 2, then 3, and so on. And a checksum. A calculation or formula is applied to the data in the packet to produce a checksum. The computer receiving the data can apply the same formula, and if the result differs from the checksum, then the data has been corrupted or damaged. Okay, these are very important things to get down because in the exam there's typically questions on the contents of a packet, so make sure you get these points down. Okay, so packet switching consists of a network of nodes. It could be servers or sometimes called packet switching centers. Data to be sent is split into packets and passed from node to node until it reaches its destination. Multiple routes can be used. If one route is busy, then it can be sent a different way. As you can see, all of the data arrive, but not necessarily in the same order. So if we see packet 2 arrives first, then packet 1, then packet 3. Packets may be received out at the destination out of sequence, so the receiving node can put them back in order using the packet sequence number. There's advantages of packet switching, so it's more efficient use of lines. Packets from different sources can be interleaved with each other. Lines are only used when packets are being sent, whereas compared with circuit switching, the lines always need to be open. They're less likely to be affected by network failure. If one line fails, there's usually other routes. So if we have a look here, if this line that packet 2 went down failed, there would be a different route for it to take because packet 1 and packet 3 took a different route than packet 2. And there's better security. Data is less likely to be intercepted because the packets are sent down multiple routes and less likely to be interleaved with other packets. So in some segments of a network, the computers may share a single cable, for example on a bus network. The computer listens to the wire to check that no packet is currently being sent. It then sends the packet. Every computer sees the packet, but only the computer referred to in the destination packet receives it, as you can see. So all the other computers saw it, but it only went to that receiving computer. If two or more computers find the line is free and start to send the packet at the same time, then the packets will be corrupted. This is called a collision. Okay, the computer sending the packets will then sense a collision has taken place and will stop sending any data. Each computer will then wait a small random amount of time, there is no fixed time limit on this, before checking the line is free and attempting to send it again. This should mean that one of them gets to send the packet before the other, avoiding another collision. The more computers that share a network segment, the more collisions occur. Okay, and then finally, we're just going to finish this video on one mythbuster. So the terms router and switch tend to be used interchangeably to describe the same types of equipment. They connect together different networks or segments of a network, receiving packets of data and passing or routing them on to the appropriate route. Okay, so that marks the end of this first video for 3.1 hardware. Come back for the second episode.